Right now, as you read these words, the universe is on fire. Not in the way a building burns, not in the way a forest catches flame and consumes itself in a single desperate night. This fire is slower, grander, and so vast that the human mind was not built to hold it. Across hundreds of billions of galaxies, each containing hundreds of billions of stars, nuclear furnaces are burning at temperatures measured in the tens of millions of degrees. Hydrogen is being crushed into helium. Energy is being released in quantities so enormous that if you converted a single second of the sun's output into a unit a human could use, it would power every city on Earth for the next several 100,000 years. And the sun is not exceptional, it is ordinary. One star among perhaps 2 trillion galaxies worth of stars, all burning, all radiating, all pouring light into the darkness. You are alive during this. That fact, which sounds simple, which sounds almost trivial, is anything but. Because here is what almost no one stops to consider. This age of fire, this era of burning stars and illuminated galaxies and warm planets where water flows and life stirs and eyes open to look upward at the night. This age is not the default state of the universe. It is not the norm. It is not what the universe looks like most of the time. It is an exception. A brief, improbable, heartbreakingly temporary exception embedded within a timeline so long that the word forever begins to feel inadequate. The universe is approximately 13.8 billion years old. That number is so large that it already defeats most attempts at intuition, but set it aside for a moment and consider a different number. The total lifespan of the universe from the first moment of the Big Bang to the last event that will ever occur in the darkness that follows stretches across something closer to 10 to the power of 100 years. Written out, that is a 1 followed by 100 zeros. Cosmologists call this number a googol, and it is so far beyond ordinary astronomical figures that even the age of the universe, 13.8 billion years, represents less than a rounding error when placed against it. The universe has barely begun, and the fire burning right now, the stars lighting every galaxy you have ever seen in every photograph ever taken, will be gone long before the universe is anywhere close to old. But here is what most people get wrong. When we speak of the death of the universe, we tend to imagine a dramatic end, an explosion perhaps, a collapse, some final violent act that brings the curtain down. The reality is far more unsettling than that, and in some ways far more beautiful. The universe will not end with a bang. It will end with a silence so complete, so total, so permanent, that the concept of ending itself will have lost all meaning. What comes is not destruction. What comes is stillness. An eternal, unbroken stillness in which nothing moves, nothing changes, nothing happens, and nothing ever will again. That is where we are going. That is the destination at the end of the road. Every star, every planet, every atom in your body is already traveling toward. If you find yourself drawn to questions that don't have comfortable answers, to journeys that take you to the edges of what is known and ask you to look beyond, then do me a small favor and hit that like button and subscribe to this channel. It genuinely helps this work reach others who are searching for the same kind of depth. And if you are already here, if you have already found your way to this particular corner of the universe, then thank you. Your presence here means something. Get yourself comfortable. What follows is not a short journey. Let's begin. To understand where the universe is going, you have to understand where it is right now. And the truth is that right now the universe is in an extraordinarily privileged moment. Cosmologists call it the Stelliferous Era, the age of stars. It began roughly 100 million years after the Big Bang, when the first stars ignited in the darkness of an infant universe, and it will last for approximately 100 trillion years from that point. 100 trillion years sounds like an eternity, but measure it against the full timeline of the universe, and you begin to see it for what it truly is. Not an eternity, a season, a warm, luminous, temporary season in a story that has barely started and will continue long after the warmth is gone. The Stelliferous Era is the only era in which life as we understand it is possible. Life requires energy gradients. It requires a source of heat and order flowing toward a sink of cold and disorder. Stars are the engines of that gradient, They pour energy outward into the cold vacuum of space and on the surfaces of the planets that orbit them. That flow of energy can, under the right circumstances, organize matter into structures of almost unimaginable complexity. Molecules, cells, nervous systems, civilizations, everything we are, everything we have ever built, or thought, or felt, exists because a star is burning nearby and we are close enough to receive its warmth, but far enough not to be consumed by it. Consider the precision of that arrangement. The sun burns at a surface temperature of approximately 5500 degrees Celsius. The Earth sits at a distance of roughly 150 million kilometers, close enough that liquid water can exist on its surface, not so close that it boils away, not so far that it freezes solid. This distance, this temperature, this balance is what makes the next sentence possible. You are here reading this thinking, that is not nothing, that is, in the context of the universe's full history, almost miraculous. But we are not the only beneficiaries of this era. The Stelliferous Age is the time when matter organizes itself into the most complex structures the universe has ever seen. A star is already extraordinarily complex, a nuclear furnace held in shape by the tension between the crushing inward pull of gravity and the outward pressure of nuclear fire. But the planets around stars can be more complex, still layered systems of rock and water and atmosphere, cycling chemicals through geological and biological processes that no purely physical system could spontaneously produce. And the life on those planets, if it arises, can be more complex still. The human brain, by some measures, is the most organizationally intricate object we have ever discovered anywhere in the universe. Not because we are special in some cosmic sense, but because the Stelliferous Era provides exactly the conditions needed to build such things. Sustained energy, stable environments, time. To feel the weight of how privileged our moment is, try this. Compress the entire lifespan of the universe from its first instant to its very last into a single calendar year. 1 year, January 1st through December 31st, representing the full sweep of cosmic time from beginning to end. On this scale, the Big Bang occurs at the very first stroke of midnight on January 1st, and the Stelliferous Era, the entire age of stars, the only era in which light fills the universe and life is possible, ends on approximately January 2nd. By January 3rd, the last star has gone dark. The remaining 363 days of the year, more than 99% of the entire calendar, unfold in darkness. No stars, no warmth, no light, just the slow, cold, patient work of entropy finishing what it started. We are living on January 1st, barely past noon. That image should change something in the way you see tonight's sky. Every star you have ever seen, every photograph of a galaxy taken by every telescope ever built, every ancient myth built around the patterns of the constellations, all of it belongs to a single afternoon in the cosmic year. The darkness that follows is not a brief night before another morning. It is permanent. The calendar has no February. Now this is the point at which the natural response is to feel something between awe and despair, and both of those feelings are appropriate. But before we follow the story into the darkness, we need to understand the mechanism. We need to understand why the fire cannot last, and why the darkness, when it comes, is so absolute. To understand that, we have to understand the force that governs the fate of everything. The force that no structure in the universe has ever escaped. No star, no galaxy, no civilization, no atom. The force that is in the deepest sense the most powerful in the cosmos. Not gravity, not electromagnetism, not the nuclear forces that hold atoms together. Something older, more fundamental, and in a way more merciless than any of those. We are talking about entropy. And to understand entropy is to understand why the universe is dying. But before we arrive there, stay for a moment longer in the warmth of this era, because the Stelliferous Age is not just the age of fire, it is the age of information, the age of structure, the age in which the universe, for the only time in its entire history, builds things. Stars forge elements heavier than hydrogen in their cores: carbon, oxygen, nitrogen, iron, everything on the periodic table beyond the lightest elements. When those stars die, they scatter those elements into space. New stars form from the enriched gas, with planets around them now carrying the raw materials for chemistry, far more interesting than simple hydrogen burning. Over billions of years, the universe bootstraps itself toward complexity, using the energy of dying stars to build the ingredients for life in the stars that follow. It is a relay race across geological time, each generation of stars passing the baton of heavy elements to the next. We are the product of that relay. The calcium in your bones was forged in the core of a star that lived and died billions of years before the sun was born. The iron in your blood was almost certainly created in a supernova explosion, a dying star's last violent act that scattered its processed elements across light years of space. The oxygen you are breathing right now was built inside stellar furnaces over and over again across the history of this galaxy before it found its way into the atmosphere of this planet and eventually into your lungs. You are not separate from the Stelliferous Era. You are its product. You are what the age of stars built when it had enough time and enough raw material. And that is why the end of this era is not merely an abstract fact about a distant future. It is personal, because when the last star goes dark, the engine that built everything we are will have burned its last gram of fuel. The forge will close. The elements have all been made. The warmth that organized them into living things will be gone. What follows is not another chapter in the same story. What follows is a different story entirely. Longer, colder, and in most respects, emptier. Now consider the stars themselves, the burning hearts of this era, more carefully. The universe contains several broad categories of stars, each with a different mass, a different temperature, a different color, and crucially, a different lifespan. And the relationship between a star's mass and its lifespan is one of the most counterintuitive facts in all of astrophysics. You might expect that a larger star would live longer the way a larger fire burns longer if given more fuel. But stars do not work that way. The more massive a star, the shorter its life. And the reason is that more massive stars burn their fuel not slowly and carefully, but in a furious, wasteful conflagration that exhausts their reserves in a fraction of the time available to their smaller, dimmer siblings. Take the most massive stars known, objects like Eta Carinae, a stellar behemoth, sitting roughly 7,500 light-years from Earth and containing somewhere between 100 and 150 times the mass of the Sun. A star like this burns so intensely that it exhausts its hydrogen supply in only a few million years. In the context of the universe's history, a few million years is nothing. It is less than the time it takes the solar system to complete a single orbit around the galactic center. These giants live brilliantly and briefly, and they die violently, often in supernova explosions, so powerful they briefly outshine entire galaxies. They are the mayflies of the stellar world, beautiful, extreme, and gone almost before they arrive. The Sun, by comparison, is far more modest. At roughly 1 solar mass, the Sun burns steadily enough to last approximately 10 billion years in total. It is currently about 4.6 billion years old, meaning it sits comfortably near the midpoint of its life. It will continue burning much as it does today for another 5 billion years before running low on hydrogen and expanding into a red giant, eventually shedding its outer layers and leaving behind a dense, cooling remnant called a white dwarf. On the cosmic calendar, the Sun is a middle-aged star, dependable, steady, not wasteful, but not eternal either. And then there are the red dwarfs. These are the most numerous stars in the galaxy, accounting for somewhere between 70 and 80% of all stars in the Milky Way. They are small, dim, cool, and extraordinarily frugal with their fuel. A red dwarf, with half the mass of the Sun, will burn for roughly 80 billion years. One with a third of the Sun's mass might burn for 200 billion years. The smallest red dwarfs, those with only about 8% of the Sun's mass, the minimum required to sustain hydrogen fusion at all, may burn for as long as 10 trillion years. 10 trillion years, a number 700 times greater than the current age of the universe. These dim, quiet stars will outlive everything else in the cosmos by an enormous margin. They will be the last lights burning when everything else has gone dark. But they will go dark too, eventually. And when they do, the Stelliferous Era will be over. The question of when that happens depends on star formation. New stars require gas, and the galaxy's supply of star-forming gas is not infinite. It is being consumed star by star, generation by generation, and the rate of new star formation has already been declining for billions of years. Astronomers have determined that the universe reached its peak rate of star formation approximately 10 billion years ago, a period sometimes called cosmic noon. Since then, the rate has been falling. The universe is forming fewer new stars each billion years than it did the billion years before. Eventually, the remaining gas will be exhausted or locked away in remnants, and no new stars will form. The ones still burning will be the last ones, and they will burn out one by one over the next tens of trillions of years, the red dwarfs going last. Each one fading slowly from orange to red to infrared to nothing. The last star will not explode. It will simply cool. Slowly over billions of years, it will dim from red to brown to black, its surface temperature dropping degree by degree until it radiates nothing detectable. There will be no fanfare, no final flash, just a gradual fading and then an absence where a star used to be, and after that absence, nothing will replace it. The raw material for new stars will be gone, the era will be over, and the universe at that point will be approximately 100 trillion years old. A number so large it makes the current age of the universe seem like the first breath of a very long sentence. What happens after that is where the story becomes truly strange, where the darkness becomes not just an absence of light, but an active, patient, grinding process of dissolution. But before we follow the universe into that darkness, we need to understand the engine driving all of it, the reason the stars burn out at all, the reason nothing in the universe lasts forever, the reason the calendar has no February. That engine has a name, and understanding it is the key to understanding everything that follows. Imagine you are holding a glass of water with a single ice cube floating at its center. The ice is cold, the water is warm. The boundary between them is sharp, clean, a clear division between order and disorder, between the concentrated cold locked inside the crystal lattice of frozen water and the warmer, more chaotic molecules of liquid surrounding it. You watch the ice. Slowly, almost imperceptibly at first, the edges begin to soften, the corners round, the flat faces become curved. The ice is melting, releasing its cold into the water around it, and the water is giving its warmth to the ice. They are moving toward each other, moving towards sameness. And when the ice is gone, when the last crystal has dissolved into the liquid, the glass will hold water at a single uniform temperature, neither as warm as it was, nor as cold as the ice. Everything will be the same throughout. No gradient, no difference, no boundary. That process, that relentless movement from difference towards sameness, from order toward disorder, from concentrated energy toward dispersed energy, is entropy. And it is not merely a property of ice cubes or glasses of water. It is the fundamental direction of everything in the universe. Entropy always wins. Not sometimes, not usually, always. In every system, in every corner of the cosmos, in every interaction between particles, in every exchange of energy, entropy increases. The second law of thermodynamics, one of the most tested and confirmed principles in all of science, states this with a clarity that leaves no room for exceptions. In a closed system, entropy can only increase or remain the same. It cannot decrease. Order cannot spontaneously emerge from disorder. The ice cube does not reassemble itself from the lukewarm water. The smoke does not pour back into the extinguished candle. The shattered glass does not leap from the floor and reassemble into a whole. These things do not happen not because of some biological or chemical limitation, but because entropy forbids them, because the number of disordered arrangements of matter and energy so vastly outnumbers the ordered ones, that the odds of spontaneous order emerging are not merely small, they are, for all practical purposes, zero. To feel the weight of what that means, think about a single drop of ink falling into a glass of clear water. At first, the ink is concentrated, a small dark cloud, expanding slowly from the point of entry. Then it begins to spread. Tendrils reach outward into the clear water. The boundary between ink and water blurs, then dissolves. Within minutes, the water is uniformly tinted. The ink has dispersed completely. And here is the question that entropy answers before you even ask it. Could you reverse that process? Could the ink spontaneously reassemble itself into a concentrated drop in the center of the glass, while the water around it returned to perfect clarity? Technically, the laws of physics do not absolutely forbid it. Every molecule of ink is simply moving according to the same physical rules, whether the ink is concentrated or dispersed. There is nothing preventing each molecule from by chance moving back toward the center at the same moment. Nothing, except the sheer improbability of it. The number of ways to arrange ink molecules in a dispersed state so vastly exceeds the number of ways to arrange them in a concentrated state that you could wait for a period of time longer than the current age of the universe, longer than many ages of the universe stacked upon each other, and the ink would never spontaneously reassemble. The direction of the process is one way. Always. The ink disperses. It does not reconcentrate. Entropy always wins. Ludwig Boltzmann understood this before almost anyone else, and it destroyed him. Boltzmann was born in Vienna in 1844, the son of a tax official raised in a city that prided itself on culture and intellectual achievement, and educated at a time when the nature of matter was still bitterly contested. The existence of atoms, the tiny particles that make up all physical matter, was not universally accepted in the scientific community of the 19th century. Many respected physicists and chemists believed that atoms were a useful mathematical fiction, a convenient way to do calculations without any commitment to their physical reality. Boltzmann believed otherwise. He believed atoms were real, that heat was the motion of atoms, that temperature was a measure of the average speed of atomic motion, and that the laws of thermodynamics, including the mysterious tendency of systems to become more disordered over time, could be derived from the statistical behavior of vast numbers of atoms moving according to simple mechanical rules. This belief drove him to one of the most profound insights in the history of physics. He proposed a mathematical definition of entropy, a formula that connected the thermodynamic disorder of a system to the number of possible microscopic arrangements of its constituent particles. His equation S equals K times the natural logarithm of W, where S is entropy, K is a constant now bearing his name, and W is the number of possible microstates corresponding to a given macrostate, is now engraved on his tombstone in Vienna. It is one of the most powerful equations in science. It says that entropy is simply a measure of how many ways a system can be arranged at the microscopic level while still looking the same at the macroscopic level. A glass of lukewarm water can be arranged in astronomically more ways than a glass of warm water with an ice cube. Therefore, the lukewarm glass has higher entropy. And since higher entropy states are overwhelmingly more probable than lower entropy states, the system will evolve toward higher entropy. Not because some force is pushing it there, but simply because there are so many more ways to be disordered than ordered that disorder is effectively inevitable. This insight, simple as it sounds, was revolutionary. It unified the mechanical world of moving particles with the thermodynamic world of heat and entropy. It explained why time seems to have a direction, why we remember the past but not the future, why eggs break but do not unbreak, why the universe as a whole is moving from its highly ordered beginning toward an increasingly disordered end. Boltzmann had glimpsed the arrow of time itself, embedded in the mathematics of probability. But the scientific establishment of his era was not ready for him. His atomism was attacked by influential figures who considered it speculative and unscientific. His statistical approach to thermodynamics was dismissed by those who preferred deterministic, continuous models of physical reality. He debated, he published, he lectured, and he was met with resistance that over the years ground him down. He suffered severe depression, what his contemporaries described as alternating periods of mania and profound darkness, likely what we would today recognize as bipolar disorder. He was brilliant and tormented in equal measure, a man who could see something true and clear and could not make the world see it with him. In 1906, while on vacation at the Bay of Duino near Trieste with his wife and daughter, Ludwig Boltzmann took his own life. He was 62 years old. Within a few years of his death, the existence of atoms was confirmed experimentally, largely through Einstein's work on Brownian motion. The thing he had fought for his entire career, the thing he had been attacked and dismissed and exhausted over, turned out to be exactly right. His equation stands today as one of the cornerstones of modern physics, but Boltzmann did not live to see it accepted. His story matters here not as a digression but as a reminder. The ideas we are talking about are not abstractions. They were fought for, lived inside, and in Boltzmann's case died beside. Entropy is not a dry textbook concept. It is the deepest truth about the physical world that science has yet uncovered, and the man who understood it most clearly paid a terrible price for that understanding. When you think about entropy, think also about Boltzmann. Alone with a truth the world was not yet ready to accept. Now, let us take entropy out of the laboratory and out of the history books and bring it into the universe itself, because the same principle that governs the ice cube in your glass governs the fate of stars, of galaxies, of everything. Entropy always wins. The universe began as best as we can determine in a state of extraordinarily low entropy. The Big Bang produced a cosmos that was hot, dense, and remarkably smooth, remarkably uniform. And while that uniformity might sound like disorder, it was in fact a kind of order, an order of sameness, with tiny quantum fluctuations rippling through it that would eventually grow under gravity into the structures we see today. Over the 13.8 billion years since, the universe has been releasing the energy stored in that initial low entropy state, allowing it to flow from hot regions to cold regions, from concentrated sources to diffuse sinks, from order toward disorder. Stars burn because they are releasing the gravitational and nuclear potential energy stored in their hydrogen, converting it into heat and light that radiate outward into the cold vacuum of space. That radiation spreads. It disperses. It dilutes. It contributes to the universe's ever-increasing entropy. Every photon that leaves the surface of every star and travels outward into the void is entropy increasing. Every nuclear reaction in every stellar core is entropy increasing. Every supernova explosion, every merger of neutron stars, every collision of galaxies is entropy increasing. The universe is spending itself, not quickly, not all at once, but steadily, irreversibly, and without exception. It is converting its low entropy initial state into a high entropy final state, one reaction at a time, one photon at a time, across billions and trillions of years. And when that conversion is complete, when every available source of energy gradient has been exhausted, when the temperature everywhere is the same, when nothing is hotter than anything else, and therefore nothing can flow toward anything else, the universe will have reached maximum entropy. And at maximum entropy, nothing happens. Nothing can happen. Because for something to happen, energy must flow, and energy only flows from hot to cold. When everything is the same temperature, the flow stops, and with the flow, everything stops. Entropy always wins. To make this concrete, think of the universe as an enormous battery. The Big Bang charged it. Every process since then has been discharging it. Stars are the most efficient discharge mechanisms we know of, converting the energy of nuclear fusion into light and heat and pouring it outward into space. But even without stars, entropy would find a way. Gravity pulls matter together, converting gravitational potential energy into kinetic energy, and then into heat when objects collide. Radioactive elements decay, releasing energy stored in unstable nuclei. Even the quantum vacuum itself, the lowest energy state of empty space, has fluctuations that participate in the universe's slow entropic evolution. There is no hiding from it. There is no process, no structure, no arrangement of matter that can permanently resist the pull toward disorder. Everything that exists is in some sense a temporary eddy in the universal flow toward maximum entropy, a brief, local, improbable moment of order that will eventually be smoothed out. You are one of those eddies. So is every living thing you have ever encountered. So is every civilization that has ever existed or will exist. So is the sun. So is the Milky Way. So is the great web of galaxy clusters stretching across the observable universe. All of it is temporary organization sustained by energy flowing from hot sources to cold sinks, destined eventually to dissolve back into the uniformity from which it was briefly drawn. Entropy always wins. But here is the thing that makes entropy bearable, that keeps it from being simply terrifying. Entropy is also the reason anything interesting ever happened. It is the reason stars shine. Stars shine because there is a temperature difference between the blazing nuclear core and the cold of space, and energy flows along that gradient outward through layers of plasma and eventually off the surface as light. Without entropy, without the drive toward disorder, that energy would have no direction to flow. The nuclear reactions at the core would occur, but produce no useful output. There would be no radiation, no warmth, no light. It is precisely because entropy is increasing, because the universe is moving toward disorder, that energy is released and made available for complex processes. Life is not a battle against entropy as it is sometimes described. Life is a process that runs on entropy. It captures the energy flowing from a hot source to a cold sink and uses it to build local order before passing the entropy downstream. A plant captures sunlight and uses that energy to build complex organic molecules from simple carbon dioxide and water. That is local order, created at the expense of the entropy increase carried away in the plant's heat and in the low-energy photons it radiates. An animal eats the plant and uses the chemical energy in its molecules to maintain its own complex structure. That too is local order, brought by the entropy increase in the animal's waste, heat, and metabolic products. Every living thing is a machine for processing entropy, taking in high-quality energy and releasing low-quality energy, building and maintaining order locally while contributing to the universe's overall disorder globally. We are in the most literal physical sense engines of entropy. We exist because entropy is increasing. We exist to help it increase. And when the sources of high-quality energy are gone, when the stars have burned their last fuel and gone dark, the engines of life will have no more feedstock. Not because life somehow failed to adapt, not because some catastrophe struck, but because the universe will have spent the energy available to drive it. The battery will be nearly flat. And in a universe with a nearly flat battery, the complex eddies of order that we call life cannot be sustained. This is not a failure. It is not a tragedy in any ordinary sense. It is simply physics, following its own rules with perfect consistency across timescales that dwarf anything human language was built to describe. The universe began with low entropy. It will end with high entropy. In between, for a brief and extraordinary interval, the energy flowing from the beginning to the end powered stars and planets and living things and thoughts, including this one, including the thought you are having right now as you absorb this. The fact that you can comprehend entropy, that you can sit here and follow the logic of why the universe is moving toward its final stillness, is itself a product of entropy. The neurons firing in your brain as you read the patterns of activation passing through your cortex, the strange loop of self-awareness that allows you to contemplate your own existence and the existence of everything around you, all of it is powered by the electrochemical gradient maintained across your cell membranes, maintained by the food you ate, maintained ultimately by the sunlight that grew the food, maintained by the nuclear fire at the heart of the sun, maintained by the gravitational collapse that formed the sun, maintained by the low entropy initial conditions of the Big Bang. The entire chain runs back to the beginning. You are a consequence of entropy, a brief, improbable, extraordinarily complex consequence of entropy, and you will return to it. But not yet. For now, the stars are still burning. The Stelliferous Era is still underway. The battery still has charge. And before we watch the last lights go out, we need to understand them more carefully. We need to understand what kind of creatures the stars are, how long each type can last, what they leave behind when they die, and which of them will be the very last to surrender to the dark. Because the story of how the Stelliferous Era ends is not a single event. It is a long, slow procession of lights going out one by one across spans of time so vast that the entire history of human civilization would be invisible against them. And at the end of that procession, one small dim red star will burn alone in a universe that has otherwise gone dark. And then it too will cool and fade and be gone. That is where we are headed next. Entropy always wins. 1426. Claude responded. There is a star in the constellation Orion that you can see with your naked eye on any clear winter night. There is a star in the constellation Orion that you can see with your naked eye on any clear winter night. It sits at the upper left of the familiar hourglass pattern, a reddish point of light that ancient observers noticed was different from its neighbors, warmer in color, slightly unsteady in its glow. Its name is Betelgeuse. It is a red supergiant, one of the largest stars known, so enormous that if it were placed at the center of our solar system, its outer surface would extend past the orbit of Jupiter. Everything inside that radius, Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter itself, all of it would be swallowed, consumed, existing inside the atmosphere of a single star. Betelgeuse is approximately 700 times the diameter of the Sun. It contains somewhere between 10 and 20 times the Sun's mass. And it is dying. Not dying in the way aging organisms die slowly and predictably across a known span of time. Dying in the way only the most massive stars can die, at the edge of catastrophic collapse, in a state of such internal instability that astronomers have spent decades watching it, with instruments across every wavelength of light waiting for the moment it crosses the threshold. Betelgeuse is expected to end its life in a supernova explosion, an event so violent that for a period of days or weeks, it will be visible from Earth in broad daylight. It will cast shadows at night. It will be, by an enormous margin, the brightest object in the sky after the Sun and Moon. And when it is over, when the explosion has faded, there will be nothing left where Betelgeuse was except a rapidly expanding shell of gas, and at its center, either a neutron star or a black hole, the compressed remnant of a stellar core that could no longer support its own weight. When will this happen? Astronomers are not certain. Betelgeuse is already in the late stages of its life, burning helium and heavier elements in its core after exhausting its hydrogen supply. The supernova could occur within the next 100,000 years, which on the cosmic scale is essentially now. It might happen tomorrow. It might have already happened, and the light of the explosion is still traveling toward us, not yet arrived. At the distance of Betelgeuse, roughly 700 light-years. Anything we observe is 700 years old. The star as it exists at this moment is unknown to us. We see only its past. That detail, that fundamental lag between event and observation, is one of the strangest features of observational astronomy. Every star in the night sky is a message from the past. The nearest star beyond the Sun, Proxima Centauri, shows us light that left it 4.2 years ago. The stars of the Big Dipper are between 60 and 120 light-years away, meaning the light you see tonight left those stars sometime between the early 20th century and the American Civil War. The stars at the edge of naked eye visibility, the faintest points you can just barely resolve on a dark night, may be showing you light from thousands of years in the past. The night sky is not a snapshot of the present. It is a mosaic of different moments in history, layered together into a single image, and Betelgeuse, brilliant and red and apparently steady in its place, may already be gone. The light will not last forever, but Betelgeuse, for all its drama, represents only one end of the stellar spectrum. It is a massive star, and massive stars are the exception, not the rule. They are brilliant but brief, burning so intensely that they exhaust their fuel in millions of years rather than billions. A star like Betelgeuse lives perhaps 8 to 10 million years from birth to supernova. The Sun, as we have noted, lives about 10 billion, and red dwarfs, the small, cool, dim stars that make up the vast majority of the galaxy's stellar population, live for timescales that make even the Sun's lifespan seem brief. To understand how the Stelliferous Era ends, you have to understand the full range of stellar lifespans, because the end of the age of stars is not a single moment, it is a procession. A long, slow dimming with the most massive stars going first, then the intermediate ones, and finally, after a wait of almost unimaginable duration, the red dwarfs. Picture the night sky of 3 billion years from now. The most massive stars currently visible, the hot blue giants that make the constellation Orion so distinctive, will be gone. They will have lived and died and been replaced by new stars forming from the gas and dust of their own remains. The constellations as we know them will be unrecognizable, their patterns shifted both by the deaths of individual stars and by the slow, proper motion of stars relative to each other across billions of years. The Sun will still be burning, but it will be noticeably brighter than it is today, having increased its luminosity by perhaps 30%, as its helium ash accumulates in its core and the hydrogen shell around it burns hotter. Earth's oceans, if they still exist, will be under severe stress from this increased radiation. Life, if it persists, will have had to adapt to conditions very different from today. Now jump forward again. 5 billion years from now, the Sun is entering the final stages of its life. Its core has exhausted its hydrogen fuel and collapsed. The outer layers have expanded dramatically, puffing outward into a red giant that swallows Mercury, then Venus, and perhaps Earth, depending on calculations that are still subject to some uncertainty. The surface of the red giant Sun, if you could stand on what remains of the Earth and look up, would fill much of the sky. The temperature on the surface of any surviving fragment of Earth would be thousands of degrees. Whatever life existed here is long gone, either evolved into forms unrecognizable to us or extinct. The Sun's red giant phase lasts only a few 100 million years, a brief flare before the outer layers are shed into space as a beautiful glowing planetary nebula, and the core left behind a dense ball of carbon and oxygen, roughly the size of Earth, but containing half the original mass of the Sun, begins its long cooling as a white dwarf. That white dwarf will not burn in any meaningful sense. It has no nuclear fuel. It is simply a hot, dense object cooling slowly into space like an ember pulled from a fire and left in a cold room. It will radiate for billions of years, growing ever cooler, ever dimmer, passing from white to yellow to orange to red to infrared, eventually becoming what astronomers call a black dwarf, an object at the same temperature as the surrounding space, emitting nothing detectable. The time required for a white dwarf to cool to that point is estimated to be longer than the current age of the universe by a factor of many thousands. No black dwarfs yet exist because the universe is not old enough to have produced one, but they are coming. Everything that makes a white dwarf today will eventually become a black dwarf, the Sun included. The light will not last forever. Now move further, much further. 50 billion years from now, 100 billion years from now, the rate of star formation has declined dramatically. The gas and dust available for new stars is being steadily consumed, locked away in stellar remnants, or expelled from galaxies by various energetic processes. Fewer new stars are forming each billion years. The galaxy is aging its stellar population, shifting toward older, dimmer stars as the bright young ones die off and are not fully replaced. The sky seen from any remaining planet is changing. The brilliant blue giants are gone. The yellow stars like the Sun are gone. What remains are red dwarfs, dim and cool, burning, with a fraction of the Sun's luminosity, emitting most of their light in the infrared, invisible to eyes calibrated for the kind of light the Sun produces. A planet orbiting a red dwarf would need to be extremely close to receive enough warmth to maintain liquid water. So close that tidal forces would likely lock one face of the planet permanently toward the star, leaving one hemisphere in perpetual scorching day and the other in perpetual frozen night. Life, if it arose on such a world, would face challenges radically different from anything we know. And yet life has proven adaptable in ways that consistently exceed expectation. It is not impossible that life persists in the universe's red dwarf era, huddled close to dim embers, invisible to any telescope we would recognize, sustained by the last reliable sources of energy in a cooling cosmos. The smallest red dwarfs burn at surface temperatures of roughly 2,000 to 3,000 Kelvin, compared to the Sun's 5,500 Kelvin. They emit a deep red light, almost ruddy, and their luminosity may be only 1,000th or 10,000ths of the Sun's output. But their frugality is extraordinary, because they are fully convective, meaning the gas in their interiors circulates continuously rather than stratifying into layers. They mix their hydrogen fuel throughout the entire star, rather than just the core. This means they can burn almost all of their hydrogen before running out, unlike larger stars that can access only the hydrogen in their cores. A red dwarf makes maximally efficient use of its fuel, and it burns that fuel at such a low rate that it can sustain the process for timescales that seem almost metaphysically long. A red dwarf with roughly 8% of the Sun's mass, the smallest viable star, will burn for approximately 10 trillion years. 10 trillion. The number is worth sitting with for a moment. The universe is currently 13.8 billion years old. 10 trillion years is roughly 700 times longer than the current age of the universe. A civilization that somehow survived until the final red dwarf entered its last billion years of life would look back at the Big Bang and find it as remote from their present as the formation of the Milky Way feels to us, and then multiply that remoteness by several hundred. The Big Bang would be ancient history of the most incomprehensible kind, and the Sun and Earth and every star currently visible in the night sky would have been gone so long that no record of them would likely survive anywhere in the physical universe. But even 10 trillion years ends. Even the most frugal red dwarf runs out of hydrogen eventually. And when it does, unlike the more massive stars, it does not expand into a red giant. It does not have enough mass for the subsequent helium-burning phase. It simply contracts. Its core, now, a ball of helium ash, continues to compress under gravity, and the star shrinks down into a helium-white dwarf, a dim object slowly cooling into darkness. No explosion, no dramatic final act. Just a gradual dimming indistinguishable from the long, slow cooling that preceded it, until the point when it is no longer possible to say whether the star is still technically a star at all. The last star in the universe will almost certainly be a red dwarf of this kind. There is no way to know which one specifically, which of the countless dim red embers burning today will be the final light. But it will go dark quietly. There will be no witness. There will be no record of it. Because by the time the last red dwarf fades, anything capable of witnessing or recording will also be gone, also profoundly transformed by time that the concepts of witnessing and recording will no longer apply. The light will not last forever. To feel what this means concretely, try this. Take the entire Stelliferous Era from the ignition of the first stars, roughly 100 million years after the Big Bang, to the extinction of the last red dwarf approximately 100 trillion years later, and compress it into a single day. 24 hours representing the entire age of stars. On this scale, the Big Bang to the first stars takes about a minute. The evolution of life on Earth, from the first single-celled organisms to the present moment, occupies approximately the last 4 seconds of the day. All of recorded human history, every civilization, every war, every scientific discovery, every work of art, every love story in the entire human record fits inside the last small fraction of the final second. The universe at this very moment, the universe that contains you and everyone you have ever known, is occurring with less than a single second remaining in the age of stars. And after that day ends, after the last light goes out, there is no second day. What follows is not darkness in the ordinary sense, the darkness of a room with the lights off, darkness you could relieve by striking a match. What follows is a darkness of a different kind, a darkness from which no light can be struck. Because the matches, all of them, will be spent. But the story does not end when the stars go out. The universe continues. It continues for a duration that makes the Stelliferous Era, all 100 trillion years of it, look like a preface. And what happens in that vast dark aftermath is stranger, and in some ways more unsettling than the simple extinction of stars. Because the remnants of the stellar age, the white dwarfs and neutron stars and black holes left behind when the fires die, do not simply sit still and wait. They are subject to the same entropic processes that killed the stars. They are subject to forces more subtle, more patient, and more thorough than nuclear burning. They will not last. Nothing lasts. And in the era that follows the death of the last star, the universe will spend incomprehensible spans of time dismantling even these remnants piece by piece, particle by particle, until nothing complex remains at all. That is where we go next. Into the long dark. Into the era that has no stars, no light, no warmth, and yet is not finished. Not even close to finished. The universe, after the Stelliferous Era, still has a story to tell. It is a colder story, a stranger story, and it is a story that will take far longer to complete than the age of stars ever did. The light will not last forever, but the dark lasts much, much longer. The last red dwarf has gone dark. The universe is now approximately 100 trillion years old. If you were somehow present in this era floating in the void between what were once galaxies, the experience would be unlike anything the human imagination has been designed to handle. There would be no stars, not a single one anywhere in any direction across the entire observable universe. The sky would be black, in a way that the word black does not adequately describe because black, as we ordinarily use it, implies a contrast. A black wall is black against a lighter room. A black sky at night is black against the stars punctuating it. But in this era, there is no contrast. There are no points of light to define the darkness by their absence. There is only the dark uniform absolute extending in every direction without interruption. And yet the universe is not empty. It is filled with objects. Countless objects distributed across the volumes that were once galaxies orbiting the gravitational centers around which they have circled for trillions of years. These objects are the remnants of the stellar age, the corpses of stars. White dwarfs slowly cooling through temperatures imperceptible to any instrument we currently possess are perhaps the most common. Neutron stars, objects of extraordinary density, the compressed cores of massive stars that ended their lives in supernovae, spin silently in the dark, their magnetic fields still active, but their surroundings now completely devoid of the material they would need to produce detectable radiation. Black holes formed from the most massive stellar remnants sit at galactic centers and scattered through the volumes of former galaxies, their event horizons unchanged, their gravity still bending whatever passes near them, which in this era is almost nothing. This is what cosmologists call the degenerate era. It begins when the last star goes dark, and it persists for a duration so vast that the Stelliferous Era, all 100 trillion years of it, is not even a meaningful fraction of it. The degenerate era lasts in rough terms from 10 to the power of 15 years to 10 to the power of 37 years. To write the upper bound of that range numerically is to write a 1 followed by 37 zeros, 1 followed by 37 zeros. The Stelliferous Era, by comparison, lasted roughly 10 to the power of 14 years. The degenerate era is therefore at minimum 10 times longer than the age of stars, and at maximum many orders of magnitude longer. It is a span of time that defeats not just intuition but any analogy designed to make it approachable. Every metaphor collapses, every comparison shrinks to nothing. You simply have to accept the number and sit with it. In this era, the slow processes that operated unnoticed during the age of stars, processes too gradual to be relevant on stellar timescales, become the dominant physics of the universe. Gravity, patient beyond any other force, continues its work. Clusters of stellar remnants interact gravitationally over trillions of years. Occasionally, two white dwarfs come close enough to merge, briefly producing a new object, and perhaps a faint flash of radiation. More often, gravitational interactions scatter individual remnants outward from their clusters, sending them drifting into the intergalactic void, while other remnants fall inward toward the black holes at galactic centers. Over unimaginable timescales, the black holes at galactic centers grow by accumulating these fallen remnants. The structures that were once spiral galaxies gradually dissolve their stars, replaced by their corpses slowly redistributed by gravity into either the surrounding void or the central black hole. Even the proton, the fundamental particle at the heart of every atomic nucleus, may not survive this era. According to some theoretical models, including several extensions of the standard model of particle physics, protons are not absolutely stable. They decay, but on timescales so enormous that no experiment has yet been able to confirm it. The current experimental lower bound on proton lifetime is approximately 10 to the power of 34 years. Some models predict it decays around that timescale, others predict longer. If protons decay, then all matter composed of protons, which is all ordinary matter, everything from white dwarfs to neutron stars to any remaining complex molecules, will eventually dissolve. Not suddenly, not all at once, but particle by particle, nucleus by nucleus, as individual protons spontaneously transform into lighter particles over the course of this incomprehensible era. If this process occurs, then by the time the degenerate era ends, there will be no white dwarfs left, no neutron stars, no atoms of any kind. Only black holes, elementary particles, and radiation. But proton decay, if it occurs, does not finish the story. Because black holes remain, and black holes for a very long time seem like the ultimate survivors. They consume everything that falls within their reach. They grow. They cannot be burned or eroded in any conventional sense. They appear at first glance to be the one structure in the universe that entropy cannot touch. But here is where one of the most extraordinary discoveries in the history of physics becomes relevant. And to tell that story, we need to talk about a man sitting in a Cambridge office in 1974, staring at equations that seemed to say something impossible. Stephen Hawking was 32 years old. He had been living with motor neuron disease for more than a decade, the illness having steadily eroded his physical capabilities while leaving his mind, if anything, sharper and more driven than before. He was already recognized as one of the most creative theoretical physicists of his generation, having made fundamental contributions to the understanding of black holes and the nature of space-time. But what he was working through, in the winter of 1974, was something different, something that did not fit neatly into any existing framework. He was trying to understand what happens when you apply the principles of quantum mechanics, the physics of the very small, to the region just outside a black hole's event horizon. Quantum mechanics had established beyond any serious dispute that the vacuum of empty space is not truly empty. At the smallest scales, space seethes with activity. Pairs of particles and antiparticles constantly pop into existence from the energy of the vacuum and annihilate each other. Almost immediately, their brief lives too short to be directly observed, but their collective effects measurable in experiments of extraordinary precision. These are called virtual particles, and they are not a theoretical abstraction. They are real in the sense that they produce measurable consequences. The Casimir effect, a tiny attractive force observed between two closely spaced metal plates in a vacuum, is a direct consequence of virtual particle pairs being excluded from the space between the plates while remaining present outside, creating a pressure imbalance. The vacuum is not nothing. It is a seething quantum froth. Hawking asked what happens to this froth at the edge of a black hole, and the answer he derived was astonishing. At the event horizon, the boundary beyond which nothing can escape, virtual particle pairs are created just as they are everywhere else. But here something unusual can occur. One particle of the pair can fall inside the event horizon while the other escapes. The escaping particle carries positive energy. The falling particle carries negative energy, effectively reducing the mass of the black hole by a tiny amount. From the outside, the effect looks exactly as if the black hole is radiating particles, slowly losing mass, slowly evaporating. Hawking showed that this radiation has a characteristic temperature, now called the Hawking temperature, which is inversely proportional to the mass of the black hole. A more massive black hole has a lower Hawking temperature and radiates more slowly. A less massive black hole has a higher temperature and radiates faster. As a black hole loses mass, it gets hotter, radiates more intensely, loses mass faster, gets hotter, still in an accelerating cycle that ends in a final burst of radiation when the black hole reaches a very small mass and essentially explodes. The result is that black holes are not eternal. They evaporate, slowly, with a patience that makes geological time seem frantic, but completely and irreversibly. The largest black holes, the supermassive objects at galactic centers weighing billions of solar masses, will take approximately 10 to the power of 100 years to evaporate completely. That number is staggering. 10 to the power of 100 years is a Google years. It is a duration so far beyond any timescale yet discussed that it renders everything that came before it, the Stelliferous Era, the Degenerate Era, even the proton decay timescale, invisible in comparison. But it is finite. It has an end. And when it ends, when the last black hole has finally radiated away its last quantum of mass, the universe will contain no black holes. It will contain the particles and radiation produced by all the evaporations that came before. And it will contain nothing else of any complexity. Hawking's discovery was not immediately accepted. It required reconciling two branches of physics, general relativity and quantum mechanics, that have never been fully unified, and the results seem to violate principles that physicists held dear. In particular, it appeared to destroy information. Information about what fell into the black hole seemed to be lost when the black hole evaporated, which contradicted a deeply held principle of quantum mechanics, that information is always conserved. This apparent contradiction became known as the black hole information paradox, and it has occupied some of the finest minds in theoretical physics for more than 50 years without complete resolution. Hawking himself changed his position on it multiple times. The debate continues. But the basic reality of Hawking radiation, that black holes slowly lose mass by radiating thermal energy, is now considered well established theoretically, even if it has never been directly observed, because for any black hole of stellar mass or larger, the Hawking temperature is so close to absolute zero that the radiation is completely undetectable against the cosmic microwave background. But consider what it means for the long-term fate of the universe. Even black holes, the apparent ultimate survivors, are subject to entropy. Even they cannot maintain their structure forever against the slow grinding of quantum processes. Entropy always wins. Not immediately, not soon in any meaningful sense. But over timescales measured in googles of years, even the most massive concentrations of matter in the universe will dissolve into thermal radiation. The black holes that seem to be the final permanent fixtures of a post-stellar universe are themselves temporary. Everything is temporary. To sit with this fact, try to imagine the universe at the moment when the last stellar mass black hole has just finished evaporating. The universe is now perhaps 10 to the power of 67 years old. The entire Stelliferous Era, every star that ever burned in every galaxy that ever existed, ended so long ago that even if you could somehow compress all of that elapsed time into a single page of text, the age of stars would occupy less than a single atom on that page. The universe is overwhelmingly incomprehensibly older than the age of stars, and it is now for the first time truly empty of all complex structures formed from ordinary matter. No atoms, no molecules, no stars, no planets, no remnants. Only radiation, individual particles drifting in an expanding void, and the supermassive black holes at former galactic centers still slowly evaporating, their Hawking temperatures still invisibly close to absolute zero, their remaining lifetime still measured in numbers that require many zeros to write. And yet, you are still in the degenerate era, in a sense. The universe is still changing, still evolving, still processing its way toward maximum entropy. The supermassive black holes are still losing mass imperceptibly slowly, but losing it. Each quantum of radiation they emit is energy escaping the black hole and spreading into the void. Each quantum of Hawking radiation is entropy increasing. The process is the same as it has always been. The scale is simply larger than anything before it. Imagine floating in this universe. If you could somehow be present, sustained against the cold and the emptiness by means impossible to specify, what would you experience? The temperature of the universe at this point is inconceivably close to absolute zero. The cosmic microwave background radiation, the afterglow of the Big Bang, has been redshifted by the expansion of the universe into wavelengths so long that detecting it would require instruments larger than any galaxy. The void in every direction is complete. No light, no warmth, no sound, of course. Sound requires a medium, and any medium has long since dispersed into individual particles, separated by distances that make intergalactic distances in our era seem intimate. The isolation is absolute. You could drift for what in our terms would be millions of years without encountering a single atom, and still the universe is not finished. Because the supermassive black holes are still there, billions of solar masses of compressed space-time, evaporating one quantum at a time, radiating at temperatures that make the coldest point in our current universe seem blazing by comparison. They are patient beyond all description. They are the last complex structures in existence, the last things that can be said to have a boundary, a location, a definable size. Everything else has dispersed, but they persist. For a Google years and beyond, they persist. And slowly, slowly, slowly they shrink. The light will not last forever, but the dark, even the dark of the degenerate era, with its cooling white dwarfs and its slowly evaporating black holes, is not yet the final dark. That comes later. That comes when the last black hole has finished its long evaporation and released its last quantum of radiation into the void. That comes when there is nothing left in the universe with any structure whatsoever, when the temperature everywhere is the same, when no object can be distinguished from any other region of space, when the final gradient has been erased and entropy has reached its maximum and nothing anywhere will ever happen again. That is the heat death of the universe. That is where we are going next. And it is stranger and in some ways more profound than anything we have yet encountered on this journey. Because the heat death is not simply the end of stars or the end of black holes. It is the end of time itself in the only sense that matters. The end of events, the end of change, the end of the possibility that anything will ever be different from what it is. Everything that exists right now in this moment, in this warm and luminous era, is moving toward that silence. Every star, every atom, every thought, including this one, the last black hole, is gone. There is no explosion to mark the moment, no flash of light visible across the universe. The final evaporation of the final black hole produces a burst of high-energy radiation, a brief quantum of energy released into the void, and then that radiation too disperses, spreading outward at the speed of light, diluting into the expanding darkness, indistinguishable within moments from the background noise of a universe that has been cooling for longer than any number in ordinary language can express. The event is in every meaningful sense unwitnessed. There is nothing left capable of witnessing it. No instrument, no eye, no mind. The universe registers its own conclusion with perfect silence. What remains is this: a vast, cold, expanding void. The universe is still expanding as it has been since the first fraction of the first second after the Big Bang, driven by dark energy, the mysterious force that permeates space and causes it to stretch. But expansion now means nothing in the way it meant something during the Stelliferous Era. When galaxies existed, expansion carried them apart, increasing the distances between structures, isolating clusters of stars from one another. Now there are no structures to carry apart. The expansion continues, but it acts on nothing. The void expands into a larger void. The darkness stretches into more darkness. Individual particles, electrons and positrons and photons and neutrinos, drift through this expanding emptiness, separated by distances that no unit of measurement developed in human history is equipped to express. The average distance between any two particles is not light years. It is not millions of light years. It is something far larger, a number that would require its own notation to write, and even then the notation would feel inadequate. The temperature of the universe at this point is extraordinarily close to absolute zero. Not absolute zero itself, because quantum mechanics and the continued expansion of space ensure that there is always some residual energy, some irreducible minimum of thermal noise. But the temperature is so close to zero that the difference between it and zero is smaller than any measurement we have ever made or are likely to make. For all practical purposes, the universe has reached thermal equilibrium. Every region of space is at the same temperature as every other region. There are no hot spots and no cold spots, no sources of energy and no sinks, no gradients. And without gradients, nothing can happen. This is the heat death, the final state of the universe predicted by the second law of thermodynamics, the inevitable consequence of entropy always increasing until it reaches its maximum possible value. The term heat death is in some ways misleading because it suggests warmth, suggests fire, suggests the kind of death that involves heat as a cause. But the heat death of the universe is the opposite of hot. It is the death that comes from the complete and total equalization of temperature, the state in which no region is warmer than any other, and therefore no energy can flow anywhere, and therefore no process of any kind can occur. It is not death by heat, it is death by sameness. Death by the final triumph of entropy over every form of order, every form of structure, every form of difference that ever existed. Physicists sometimes call this state maximum entropy or thermodynamic equilibrium. In ordinary life, equilibrium sounds pleasant, a state of balance, of rest of things being in their proper proportion. But thermodynamic equilibrium at the scale of the universe is not pleasant. It is not restful in any sense a living thing could appreciate. It is the state in which nothing is possible. Not merely difficult, not merely unlikely, impossible, because every process, every event, Every change of any kind requires a difference. It requires one thing to be different from another, warmer than, colder than, higher energy than, lower entropy than. Without difference, without gradient, without asymmetry of any kind, the universe has nothing to work with. It is a machine with no fuel, an engine with no temperature, differential a river with no slope. The water does not flow because there is no downhill. Everything is flat. Everything is the same. And sameness at this scale is indistinguishable from nothing. Entropy always wins. And this is what winning looks like. Now, here is where the story becomes strange, in a way that even the timescales of the degenerate era did not prepare us for, because the heat death is not an ending in the sense that the death of a star is an ending. A star ends. It exhausts, its fuel collapses, explodes or fades, and leaves a remnant. There is a before and an after, a clear transition between one state and another. The heat death has no after in that sense. It is not a transition. It is a permanent condition, a state the universe enters and never leaves, not for 1 billion years, not for a Google years, not for any number of years that can be written in standard notation or in any notation. The heat death once achieved is forever. The universe at maximum entropy is not waiting for something. It is not resting between events. It is simply in a state in which events do not occur, have not occurred for longer than any time scale we have yet discussed, and will not occur again. Or will they? This is where one of the most disturbing ideas in all of cosmology enters the picture. An idea that emerges not from observation or experiment, but from the relentless application of probability theory to a universe that, despite being at maximum entropy, is not quite nothing. The idea is called the Boltzmann Brain, and it is named with a certain grim irony after the same man whose understanding of entropy we traced earlier. Ludwig Boltzmann, in his efforts to understand the statistical nature of thermodynamics, grappled with a puzzle. If the universe tends toward maximum entropy, why does it currently appear to be in a state of relatively low entropy? Why does order exist at all? One answer he considered and later rejected was that the observable universe might be a random fluctuation in an otherwise featureless high entropy cosmos, that by chance an enormous region of space happened to fluctuate into a state of low entropy, and we find ourselves inside that fluctuation simply because it is the only kind of region in which observers can exist. This idea applied to the heat death scenario leads somewhere deeply unsettling. In a universe at maximum entropy with a temperature infinitesimally above absolute zero, quantum fluctuations still occur. They must. Quantum mechanics does not allow for perfect stillness even at the lowest energies. In any region of space, particles can spontaneously appear and disappear. Energy can fluctuate briefly above and below the equilibrium value. Random configurations of matter and radiation can form and dissolve. Almost all of these fluctuations are vanishingly small and vanishingly brief, a few particles appearing and disappearing in a tiny region of space. But in a universe that persists for a truly infinite amount of time, even extraordinarily improbable events will eventually occur. And the question becomes, what is the most improbable event that quantum fluctuations could produce? Here is the answer that makes physicists uncomfortable. Given enough time, truly enough time, timescales that make a Google years look like a heartbeat, a quantum fluctuation could in principle spontaneously assemble something more complex than a few particles. It could assemble purely by chance a structure complex enough to be a functioning brain, a brain complete with false memories of a life of experiences, of a universe that seems real, but is in fact simply the content of a randomly assembled neural structure, flickering briefly into existence from the quantum noise of a dead universe before dissolving back into equilibrium. This spontaneously assembled mind is the Boltzmann brain. The probability of such an event is incomprehensibly small. It would require an almost perfect alignment of quantum fluctuations across an enormous number of particles, all organized in exactly the right way to produce a structure capable of thought. The time scale required for it to occur even once, even in a region of space the size of our observable universe, is so large that it makes the evaporation time of a supermassive black hole look like a brief intermission. But in a universe that persists forever, or something close to forever, even this probability multiplied by infinite time produces a result. Boltzmann brains will occur, perhaps infinitely many of them. Random minds flickering into existence from the quantum noise of a dead cosmos, experiencing a moment of awareness, perhaps a moment of terror, or wonder, or confusion, and then dissolving back into the equilibrium from which they briefly emerged. Are you a Boltzmann brain? The question is not entirely frivolous. If Boltzmann brains will eventually outnumber ordinary observers by an incomprehensible margin, then the most probable kind of mind in the universe's full history is not a mind that evolved through billions of years of biological complexity on a planet orbiting a star. It is a mind that appeared randomly from quantum noise fully formed, complete with false memories of exactly the kind of life and world that you seem to remember. If the Boltzmann brain scenario is correct, then the probability that you are one is astronomically higher than the probability that you are what you seem to be. Most physicists find this conclusion unacceptable, not because it is frightening though it is, but because it is scientifically incoherent. A Boltzmann brain, by definition, could not trust any of its apparent observations or memories. Its apparent experience of a consistent, lawful universe would be a coincidence, not a reflection of reality. Science requires that observations be trustworthy, that the universe we observe is real and consistent. If Boltzmann brains dominate, science itself becomes impossible because no observer can know whether their observations reflect the real world or are simply the random content of a spontaneously assembled mind. The fact that science works, that the universe behaves consistently and lawfully, is taken by many physicists as evidence that we are not Boltzmann brains, and therefore as evidence that the cosmological models producing Boltzmann brains in large numbers must be incomplete or incorrect. But the deeper point survives regardless. In a universe at or near maximum entropy, persisting for timescales approaching infinity, the ordinary rules of what is possible and what is not become strange. Events of extraordinarily low probability are not ruled out. They are merely delayed, and delayed in this context means delayed by durations that no clock could measure, because no clock could survive to measure them. The heat death is not a tidy ending. It is an open-ended condition, infinite in duration, in which the laws of physics continue to apply even when nothing is happening, in which probability theory still generates predictions even when no one is present to make observations, in which the universe persists in a state that is the closest thing to nothing that something can be. This is the final answer to the question of what happens to the universe. Not a bang, not a collapse, not even a gradual fading, though that is part of the story. The final state is equilibrium, uniformity. A state of maximum entropy in which the temperature everywhere is the same, in which no energy flows from anything to anything, in which no event of any kind occurs, in which the universe simply is in a condition indistinguishable from most profound silence imaginable forever. Entropy always wins. And yet, there is something that this picture, this cold and patient ending, does not account for. Something that the equations of thermodynamics and the timescales of cosmic evolution do not touch. There is the fact that right now, at this moment in the extraordinarily brief and luminous era we inhabit, something extraordinary is happening, something that will not happen again for timescales beyond any we have discussed, something that in the context of the universe's full history is so rare and so improbable and so fleeting that the word precious, however inadequate, is the closest language can come. The universe is being observed, not by instruments, not by abstract measuring devices, by minds, by beings that evolved from the matter of dying stars on the surfaces of warm planets powered by the energy of nuclear fire, who can look outward at the darkness and understand what they see, who can trace the arrow of entropy backward to the Big Bang and forward to the heat death, who can hold the entire sweep of cosmic time in their awareness, from the first instant of creation to the final silence, and feel something about it. Awe, sorrow, wonder, gratitude, the specific flavor of beauty that comes from understanding how temporary a thing is. You are one of those beings, and you are doing exactly that right now. That fact, simple as it sounds, is the most improbable thing in the universe's entire history, not the formation of stars, not the synthesis of heavy elements, Not even the emergence of life, extraordinary as all of those are. The most improbable thing is this: that matter, organized by entropy and time into the specific configuration that produces self-awareness, is sitting here in the brief warmth of the Stelliferous Era, following the logic of its own dissolution and finding it beautiful. The heat death is real, the timeline is real, the silence at the end is real, but so is this moment. And this moment, measured against the full duration of the universe, is so brief that every analogy we have used fails to capture it. It is not a second in a day. It is not a heartbeat in a lifetime. It is something smaller than that, something for which there is no comparison, because the timescales involved exceed any framework in which comparisons make sense. We are here for an instant, a blinding, warm, improbable instant in a story that will continue in darkness for far longer than we can think. That is not a reason for despair. It is a reason for something closer to reverence. But before we arrive at that conclusion, before we settle into the weight of what it means to be a conscious thing in a universe trending toward its final silence, we should be honest about the uncertainty in everything we have discussed. Because the heat death, for all its theoretical support, is not the only possible fate the universe might face. Other scenarios exist. Other endings have been proposed, and some of them are stranger than the quiet equilibrium of maximum entropy. Some of them are more violent, some of them are more final, and all of them deserve to be heard before we decide what we believe about where the universe is going. 1431, Claude responded. Science is not a collection of final answers. Science is not a collection of final answers. Ruthanus, of building better and better approximations of reality, each generation of understanding more precise and more complete than the last, but none of them permanent, none of them beyond revision. The history of physics is littered with theories that seemed unassailable and turned out to be incomplete. Newtonian mechanics described the motion of planets with extraordinary accuracy for 2 centuries before Einstein showed that it was an approximation valid at low velocities and weak gravitational fields, but breaking down at the extremes. Classical electromagnetism seemed to describe all of electrical and magnetic phenomena, until quantum mechanics revealed that at small scales the picture was radically different. Even general relativity, our best current theory of gravity and space-time, is known to be incomplete because it breaks down at the singularities inside black holes, and at the moment of the Big Bang, precisely the conditions where a complete theory of quantum gravity would be needed. So, it is entirely reasonable to ask, when confronted with the picture of heat, death, and entropic dissolution we have been building, whether this too might be incomplete, whether some future theory might reveal a mechanism that entropy missed, a process that could restore order from disorder, a loophole in the second law that allows the universe to escape its apparent fate. This is not wishful thinking, it is good scientific instinct, and it deserves a serious answer. The natural response is to imagine a universe far more creative than our current models suggest, one that finds ways to renew itself, to cycle through death and rebirth, to escape the one-way arrow of entropy through some mechanism we have not yet discovered. No. And this is the point that casual speculation about cosmic futures consistently misses. The second law of thermodynamics is not a provisional approximation in the way that Newtonian mechanics was provisional. It is not a description that works well in ordinary circumstances but might break down at extremes. It is a statistical statement about the overwhelming probability of disordered states compared to ordered ones, and that statistical reality does not depend on the specific physics of any particular theory. It depends on mathematics, on the simple fact that there are incomparably more disordered arrangements of matter and energy than ordered ones in any syndrombic we can conceive of. Even if general relativity is replaced by a complete quantum theory of gravity, that theory will still operate in a universe where disordered states vastly outnumber ordered ones. Entropy will still increase. The arrow of time will still point in the same direction. The heat death, or something functionally equivalent to it, will still be the destination. But that does not mean there are no alternative endings worth examining, because while entropy sets the direction, it does not fully specify the path. And depending on properties of the universe that we do not yet know with certainty specifically, the nature and behavior of dark energy, the journey to maximum entropy, might take radically different routes. Some of those routes are considerably more violent than the quiet equilibrium we have been describing. The first alternative is called the Big Rip. It emerges from a particular model of dark energy in which the energy density of the vacuum does not remain constant as the universe expands, but instead increases over time. In our current best model, dark energy behaves like a cosmological constant, a fixed energy per unit volume of space that remains unchanged as space expands. This is what drives the accelerating expansion we currently observe, and on this model, the expansion continues forever, but never becomes so extreme as to tear apart bound structures. Galaxies remain intact, solar systems remain intact, atoms remain intact. The universe expands into a larger and larger void, but its internal structures are held together by the forces that bind them. But if dark energy is not a constant, if it grows stronger as the universe expands, then the expansion itself accelerates without limit, and a sufficiently rapid expansion will eventually overcome every binding force in the universe. First, galaxy clusters are torn apart as the expansion overwhelms gravity on the largest scales. Then individual galaxies are shredded, then solar systems, then planets, then individual objects, then molecules, then atoms, then, in the final fraction of a second before the endpoint, even atomic nuclei are torn apart as the expansion overwhelms the strong nuclear force itself. The universe ends not in a long, patient cooling, but in a violent, simultaneous ripping apart of every structure at every scale, all at once, everywhere. The Big Rip. Current measurements of dark energy suggest that it behaves approximately like a cosmological constant, which disfavors the Big Rip. But the measurements are not precise enough to rule it out entirely. The parameter that determines whether the Big Rip occurs, called W, pi, the equation of state parameter for dark energy, needs to be more negative than -1 for the Big Rip to happen. Current data place W very close to -1, consistent with a cosmological constant, but with error bars that allow values slightly more negative. Future observations, particularly from missions designed to map the expansion history of the universe with greater precision, may narrow these error bars enough to tell us definitively whether the Big Rip is possible. For now, it remains a genuine alternative, disfavored but not excluded. The second alternative runs in the opposite direction. Where the Big Rip imagines an expansion that accelerates without limit, the Big Crunch imagines an expansion that eventually reverses. If the total energy density of the universe exceeds a critical threshold, gravity can overcome the expansion and pull everything back together. The universe would slow halt and then contract, galaxies falling toward each other, temperatures rising as matter and radiation are compressed, until the entire universe collapses back into a state of extreme density and temperature, a mirror image of the Big Bang. This is the Big Crunch. For most of the 20th century, the Big Crunch was considered a serious possibility. The question of whether the universe would expand forever or eventually collapse was one of the central open questions in cosmology, and it hinged on measurements of the total matter and energy density. Then, in 1998, two independent teams of astronomers studying the brightness of distant supernovae made a discovery that effectively ruled out the Big Crunch in the simplest models. They found that the expansion of the universe is not slowing down, as it would need to if gravity were eventually going to win, but accelerating. Dark energy is pushing space apart faster and faster over time. In a universe dominated by dark energy, the Big Crunch cannot happen unless dark energy itself eventually changes character in a way that reverses its repulsive effect. Nothing in current observations suggests this is occurring. The Big Crunch is not entirely dead as an idea. Certain theoretical models, including some approaches to quantum cosmology, allow for scenarios in which the current expansion is a phase that will eventually end and reverse. But these models are highly speculative and lack observational support. The Big Crunch, which once seemed like a perfectly reasonable fate for the universe, has been pushed to the margins of cosmological possibility by the discovery of dark energy. The third alternative is perhaps the most philosophically intriguing. It is called the Big Bounce. The Big Bounce takes the Big Crunch seriously and asks what happens next. If the universe collapses to extreme density, does it simply end, or does the collapse somehow trigger a new expansion? In some models of quantum gravity, the singularity that classical general relativity predicts at the endpoint of a Big Crunch is avoided by quantum effects that cause the collapse to bounce, producing a new, expanding universe from the remnants of the old one. This would make the universe cyclic, passing through endless sequences of expansion, collapse, and rebirth, with each cycle potentially producing a universe with slightly different physical properties. Loop quantum cosmology, a theoretical framework that applies quantum mechanics to the structure of space-time itself, provides one mathematical realization of this idea. In loop quantum cosmology, the Big Bang itself is understood as a big bounce, a rebound from a previous collapsing universe. The universe did not begin from nothing. It was born from the collapse of something that came before. And if this framework is correct, then our universe too will eventually collapse and bounce, giving rise to a successor universe that will never know we existed. The Big Bounce is intellectually appealing because it solves, or at least sidesteps, the problem of ultimate origins. If the universe cycles endlessly, then there is no first moment, no creation from nothing, no need to ask what existed before the Big Bang. The answer is simply a previous universe. But the Big Bounce faces serious challenges. Chief among them is exactly the problem entropy poses. If the universe cycles through expansion and collapse, each cycle should have higher entropy than the last, because entropy always increases and collapses do not reset it. Over many cycles, the universe should become progressively more disordered, which means the cycles themselves should change in character over time. A cyclic universe of this kind cannot be truly eternal in both directions. It must have had a beginning somewhere, even if each individual cycle is preceded by another. The entropy problem does not go away. It merely retreats one step. And then there is the possibility that escapes the framework of any single universe entirely. The idea of a multiverse in which our universe is one of a vast or infinite number of separate universes, each with its own physical laws, its own constants, its own history. In some versions of inflationary cosmology, the process that drove the rapid expansion of the early universe produces not one universe, but an endless proliferation of them, each bubble universe nucleating from the inflationary background and expanding into its own separate existence. In string theory, the landscape of possible universes is so vast that virtually every possible combination of physical laws is realized somewhere. On these views, the heat death of our universe is not the end of everything. It is the end of one universe among countless others, each following its own trajectory, some perhaps ending in heat death, some in big rips, some collapsing, some persisting in ways we cannot imagine. The multiverse is at present beyond the reach of direct observational test. If other universes exist, but are causally disconnected from ours, no signal can pass between them, and no observation we can make can confirm or deny their existence. This places the multiverse in a philosophically uncomfortable position. It may be correct. It may be the deepest truth about the structure of reality, but it may also be forever outside the reach of science as we practice it. Some physicists embrace it enthusiastically as the natural consequence of our best theories. Others reject it as metaphysics rather than physics, a story we tell to avoid confronting the strangeness of a universe with a beginning and an end. What can we say with confidence? We can say that the heat death, the quiet equilibrium of maximum entropy, remains the best supported prediction for the long-term fate of the universe within our current theoretical framework. Dark energy appears to be approximately constant, which rules out the Big Rip in the simplest models. The accelerating expansion rules out the Big Crunch without exotic modifications to dark energy. The Big Bounce faces the entropy problem that prevents a truly cyclic eternal universe. And the multiverse, whatever its merits, does not change the fate of our particular universe, which on any of these accounts ends in some version of maximum entropy. The second law of thermodynamics is the most reliable guide we have. Not because it is certainly correct in every detail, but because it reflects a mathematical truth about the relationship between order and disorder that is deeper than any particular physical theory. Whatever replaces general relativity and quantum mechanics in our future understanding of physics will still operate in a universe where disordered states vastly outnumber ordered ones. Entropy will still increase. The direction of time will still be defined by that increase, and the universe will still move relentlessly and without exception toward the state of maximum entropy. Entropy always wins. This is not pessimism. It is not a counsel of despair. It is the honest acknowledgement of what the physics tells us, held alongside the equally honest acknowledgement that we do not know everything, that our theories are incomplete, and that the future of science may reveal aspects of reality we cannot currently imagine. Both of these things can be true at once. The universe is probably heading toward heat death, and we do not know everything about the universe. These are not contradictions. They are simply the two poles of intellectual honesty about a question of extraordinary difficulty. But here is what strikes me as more important than any of these alternative scenarios. More important than the big rip or the big crunch or the big bounce or the multiverse. Whatever the ultimate fate of the universe, whatever ending the physics eventually delivers it, does not change the fundamental character of our situation. We are here now, in the warm, luminous, improbable middle of the Stelliferous Era, surrounded by stars, warmed by one, alive on a planet that has been building toward this moment for 4.5 billion years, possessed of minds capable of tracing the arc of cosmic history from the first instant of creation to the last possible event in a dead and frozen cosmos, and asking in full awareness of everything we have just discussed, what any of it means. That question does not have a scientific answer, but it has an answer, and it is the only place left to go on this journey, back to the beginning, back to the moment we started, back to the warmth. Step outside tonight, if you can. Find a place where the sky is dark enough to show you stars. Stand still for a moment and let your eyes adjust. Let the darkness settle around you, and the points of light emerge first, the brightest ones, then the fainter ones, then the faintest, the ones at the edge of visibility that you can only see by looking slightly to the side of them, the old trick of peripheral vision that astronomers have used for centuries. Let the sky fill with them, and then simply look. What you are seeing is fire. Not metaphorical fire, not fire in the poetic sense of something bright and passionate and brief. Actual nuclear fire burning at temperatures of tens of millions of degrees, sustained by the crushing pressure of stellar gravity, forcing hydrogen nuclei together with enough force to overcome their mutual repulsion and fuse into helium, releasing in the process the energy that has been crossing the void between you and that star for years, decades, centuries, millennia, depending on which star you are looking at. The light entering your eyes right now left its source before you were born. Some of it left before your parents were born. Some of it left before the first human civilization scratched marks into clay. You are receiving in this moment messages from the deep past carried at the fastest speed the universe permits, arriving now, here at your eyes, at your mind. That is what the night sky is, not decoration, not backdrop. A delivery of ancient fire across impossible distances to a pair of eyes that evolved over 4 billion years of biological trial and error, precisely the sensitivity to detect it. We began this journey with a simple and devastating fact. The universe is on fire right now, burning across hundreds of billions of galaxies, pouring light into the darkness, with a profligacy that feels eternal but is anything but. We have followed that fire forward in time, watching it cool and dim, and eventually go out star by star across timescales that defeat every attempt at intuition. We have watched the last red dwarf fade. We have watched the white dwarfs cool to black. We have watched the black holes evaporate, quantum by quantum, across durations measured in googles of years, until even the last complex structure in the universe dissolved into the thermal noise of a cosmos at maximum entropy. We have arrived at the heat death, the final silence, the state from which no return is possible and in which nothing anywhere will ever happen again. And now we are back in the warm, back in the light, back in the only moment that any of this is real to anyone. Here is what we know. The Stelliferous Era, the age of stars, the only era in which the universe contains light and warmth, and the possibility of life will last approximately 100 trillion years from beginning to end. The universe's full timeline from the Big Bang to the final evaporation of the last black hole extends to something approaching 10 to the power of 100 years. The age of stars measured against that full timeline occupies a fraction so small that expressing it as a percentage is meaningless. It is a sliver, a flash, a brief incandescence in a story that is overwhelmingly about cold and darkness and silence. We are living in that flash, not near its end, near its beginning. The universe is 13.8 billion years old. The Stelliferous Era will last 100 trillion years. We are on the timeline of the age of stars, approximately where a person would be who has been alive for 6 hours in a life that will last 5,000 years. We are infants in the age of fire. The overwhelming majority of the time during which stars will burn and planets will orbit, and the conditions for life will exist in the cosmos. That time is still ahead. The universe's productive era, its warm and luminous season has barely begun. That thought does not diminish the darkness that follows. The heat death is still coming. Entropy still wins. The silence at the end is still absolute and permanent, but it reframes where we stand in the story. We are not witnessing the end of the fire. We are witnessing its morning, and we are witnessing it consciously. This is the fact that stops me every time when I follow this chain of reasoning to its conclusion. Out of all the possible arrangements of matter and energy that the universe could have produced in its first 13.8 billion years, it produced at least one arrangement capable of understanding what it is, at least one configuration of atoms, organized by evolution and chemistry and time, that can trace the arc from Big Bang to heat death and feel the weight of it. That can hold the concept of a Google years in mind and experience something in response to it. Not just process it, feel it. You are that arrangement. The atoms in your body are almost as old as the universe itself. The hydrogen in the water in your cells was forged in the first 3 minutes after the Big Bang, when the universe was hot enough and dense enough for protons and neutrons to fuse into the lightest nuclei. The heavier elements, the carbon that forms the backbone of every biological molecule, the oxygen you are breathing, the iron carrying oxygen through your blood, were forged in stellar interiors and scattered by stellar deaths across billions of years. Every atom that makes up your body has been part of the universe for most of the universe's history. Some of those atoms have been part of stars. Some have drifted through interstellar space. Some have been locked in rock, dissolved in ancient oceans, incorporated into organisms that lived and died long before the first human stood upright. You are not separate from the universe looking at it from the outside. You are the universe looking at itself from the inside. You are what the Stelliferous Era produces when it is given enough time and enough chemistry and the right conditions. You are matter that has learned to contemplate its own dissolution, and in this moment you are doing exactly that. The light will not last forever. We have established that beyond any reasonable doubt. Every star currently burning will eventually exhaust its fuel and go dark. Every white dwarf will eventually cool to absolute cold. Every black hole will eventually evaporate. Every atom of ordinary matter, if proton decay occurs, as some theories predict, will eventually dissolve into lighter particles and radiation. The universe is spending itself, and the spending is one way. There is no mechanism for renewal that physics currently supports. The entropy that drives the stars to shine is the same entropy that will, given time enough, reduce the universe to featureless equilibrium. But consider what that fire has already done. In the time between the Big Bang and this moment, the universe's burning stars have forged every element on the periodic table. They have illuminated billions of galaxies, each containing hundreds of billions of worlds. They have powered the chemistry that produced life on at least one planet, and almost certainly on others, though we have not yet found the evidence. They have provided the energy that drove 4 billion years of biological evolution on Earth, from the first self-replicating molecules in ancient oceans to the organism reading these words right now. They have given us minds capable of understanding quantum mechanics, general relativity, thermodynamics, and the arrow of time. They have given us the capacity to ask what it means that all of this is temporary. That last gift is the most extraordinary. The capacity for meaning is not something physics predicts or explains. It emerges from complexity, from the specific organization of matter that produces consciousness. And consciousness is itself a product of the Stelliferous Era's generosity. Without stars, no heavy elements. Without heavy elements, no chemistry. Without chemistry, no biology. Without biology, no minds. Without minds, no meaning. The entire chain runs back to the first ignition of the first star in the darkness of the infant universe. Meaning itself is a gift of stellar fire. And what meaning can we make of what we have learned? Perhaps this: the universe does not owe us permanence. It does not owe any structure permanence. Stars are temporary, galaxies are temporary, black holes are temporary. The laws of thermodynamics do not grant exemptions. But the fact that something is temporary does not diminish its reality while it exists. The ice cube melting in the glass of water is no less real for melting. The fire burning in a hearth is no less warm for going out. The star shining across 4 light-years of void is no less a furnace of extraordinary violence and beauty for having a lifespan measured in billions of years rather than forever. And you reading this are no less real, no less significant, no less worthy of your own existence for being a temporary arrangement of atoms in a universe trending toward equilibrium. The Stoic philosopher Marcus Aurelius wrote almost 2,000 years ago that the life of a man is a point in time, its substance, a river in flux. Its perception clouded the composition of the body, subject to easy putrefaction. He was not speaking of thermodynamics. He did not know about entropy or the heat death or the Google-year timescale of black hole evaporation, but he had grasped something true about the relationship between impermanence and meaning. The fact of impermanence is not the enemy of meaning. It is the condition of meaning. Things matter precisely because they do not last. A universe in which nothing ever changed, in which no process ever completed, in which entropy never increased and nothing ever moved from one state to another, would be a universe in which nothing ever happened. And a universe in which nothing ever happens is a universe without meaning of any kind. It is entropy that makes the fire burn. It is entropy that makes the warmth flow from the star to the planet. It is entropy that drives the chemistry of life. It is entropy that makes time move in a direction that makes causes precede effects, that makes experience possible. Without entropy, without the relentless increase in disorder, none of this could exist. We do not live despite the fact that the universe is running down. We live because it is running down. We are the running down, made conscious of itself. Entropy always wins, and in winning it, produced you. Now consider the view from where we stand. We are in the early morning of the Stelliferous Era, surrounded by the fire of hundreds of billions of galaxies. The night sky above us is not a ceiling. It is a window into a burning cosmos, and every point of light in that window is a nuclear furnace maintaining itself against the pull of gravity, contributing its energy to the universe's slow entropy, and in doing so, keeping conditions for complexity, for chemistry, for life, for mind, sustained for a little longer. Each star is a temporary island of low entropy in a universe trending toward maximum entropy. Each one is fighting a losing battle with extraordinary grace. The sun is fighting that battle right now. Every second it converts approximately 600 million tons of hydrogen into helium, releasing the energy difference as light and heat that radiates outward in all directions. A tiny fraction of that energy, an almost inconceivably small fraction, strikes the Earth. An even tinier fraction of that strikes the surface where photosynthesis can use it. An even smaller fraction still makes its way through the chain of biology and chemistry and evolution into the neurons firing in your brain as you process these words. You are running on starlight. You have always been running on starlight. The thinking you are doing right now is powered by nuclear fusion happening 93 million miles away. That connection from stellar core to conscious mind is real. It is physical. It is not a metaphor. The energy in the photons that left the sun 8 minutes ago is the energy moving through your nervous system at this moment. You are not watching the universe from a distance. You are continuous with it. You are made of it and powered by it, and will return to it when the atoms that currently form your body eventually disperse and become part of other things, other arrangements, other processes in the long story of this temporary and extraordinary era. The last star will go dark. In approximately 100 trillion years, the final red dwarf will cool to black, and the Stelliferous Era will end. The darkness that follows will last for durations that make 100 trillion years look like an introduction. The heat death, when it arrives, will be permanent. The silence will be absolute, and in that silence there will be nothing left that can ask what it meant. Nothing left that can remember that there was ever a time when the universe was warm and bright and full of fire. But it will have been true. The warmth will have been real. The light will have been real. The minds that briefly held the universe in their awareness and found it beautiful and terrifying and worthy of the deepest attention they could give it, those minds, will have been real. The trueness of it does not depend on its permanence. The fire does not become less real because it goes out. The warmth does not become less warm because it fades. Reality is not contingent on duration. And so, we return to where we began, to the universe on fire right now in this moment, burning across hundreds of billions of galaxies, with a prodigality that feels eternal. It is not eternal. We know that now. But we also know something we did not know at the beginning of this journey. We know how rare this moment is. We know how brief the fire is against the full sweep of cosmic time. We know that the silence which follows will last so much longer than the burning, that the burning is, by any measure, a miracle of improbability. And we are inside that miracle, not watching it from the outside, living inside it, made of it, powered by it, aware of it. Look up at the stars again. Each one is a temporary low-entropy island in a universe that will outlast it by durations beyond imagination. Each one is fighting the same losing battle with the same extraordinary grace. Each one is contributing its fire to the brief, warm season of the cosmos, the season that produced the conditions for everything you are, everything you have known, everything you have loved. You are a consequence of starfire. You are matter organized by 4 billion years of entropy-driven chemistry into a shape complex enough to ask where it came from and where it is going. You are the universe's way of knowing itself briefly, imperfectly, with the specific limitations of a nervous system evolved for a very different purpose, but knowing itself nonetheless. The fire will not last forever. The light will not last forever. The warmth will not last forever. But right now, in this extraordinary and improbable morning of the Stelliferous Era, the fire is burning. The light is crossing the void. The warmth is here on this world in this moment, in the specific and unrepeatable configuration of matter and energy that is you reading this, thinking this, feeling this. It is extraordinary, it is temporary, and it is awes. A single candle burning in a darkness that will last longer than any number has yet been invented to express. That is what we are. That is what every mind that has ever looked up at the night sky and wondered has been. Not diminished by the darkness that surrounds it, not made meaningless by the darkness that will eventually swallow it, made precious by it, made rare by it, made worth the noticing. The candle is burning now. Notice it.